So, now we are going to solve some examples in kinetics to help you understand with the concepts. Okay. So, the first example that we take here is that a Cauchy stress at a point is given by following form where A1, A2, A3 are constants, okay. And then you have to find the constraints on A1 and A3, so that the solution exists for a plane which is parallel to the x3 axis, such that the traction vector is tangential to this plane. Okay. Now, since normal is not given to us, the first thing we have to do is to find out the normal. Before we can apply the Cauchy stress principle, that is T equal to sigma n, we need to find out n. Okay. So, we have been given that the plane is parallel to x3 axis, which means that the normal on the plane which is parallel to E3 axis, okay, can be written as, let us say n, normal is n1, n2, n3, okay, in the component form, then n dot E3 will be equal to 0, which means that n3 will be equal to 0, which means my normal vector will be of the form n1, n2 and 0. Okay. n1, n2 are still unknown, that we need to find out. However, once we have the normals and I have my Cauchy stress tensor, what I can do now is I can find out the traction on a plane using the following Cauchy stress principle, that is the traction on a plane having a normal n is nothing but sigma n. Okay. Once I have this, I can substitute for sigma and n from the previous slides. Okay. So, this is my sigma and this is my n, and when I substitute this from the previous slide, I get the following expression for the traction and the traction vector, okay, and there are 3 components. Okay. Now, to find out n1 and n2, which are unknown here, we assume that a1, a2, a3 are all known, okay, they are arbitrary, but known at this point. So, to find out n1, n2, we also consider that we have been given that the traction is tangential to the plane, which means that T dot n is equal to 0. So, if I just take dot product of this, that is transpose of this with n1, n2 0, I get a1 n1 square plus a3 n2 square equal to 0. Okay. So, this is first equation that I have to solve for n1 and n2. The second equation can be obtained by considering the fact that this normal has to be a unit normal, which means that n1 square plus n2 square should be equal to 1. So, now I have 2 equations in n1 square and n2 square. Okay. So, I can solve for n1 square and n2 square, and then I can get my normal vector n as following. It is root over a3 divided by a3 minus a1, root over minus a1 upon a3 minus a1, and obviously the third component was 0. Okay. With this, I can now establish the constraint on the terms on the constants a1 and a3. Okay. So, let us see the first component. Okay. Obviously, if this first component has to exist, which is equal to n1, then root of a3 upon a3 minus 1 has to exist, which means that a3 minus a1 has to be greater than 0, otherwise you will have a imaginary value. That cannot exist, that cannot happen. So, a3 upon a3 minus a1, which is here, has to be greater than 0. So, there are 2 ways in when a3 upon a3 minus a1 can be greater than 0. The first, if a3 is greater than 0, then obviously a3 minus a1 has to be greater than 0 for this ratio to be greater than 0. Now, if a3 is less than 0, then a3 minus a1 has to be less than 0. This implies a3 is greater than a1, and this implies a3 is less than a1. Okay. So, the first constraint on a1 and a3 are, if a3 is greater than 0, then a3 has to be greater than a1, and a3 is greater than 0, less than 0. So, a3 has to be less than a1. Now, consider the second component. So, here minus a1 upon a3 minus a1 has to be greater than 0, which means that minus a1, if minus a1 is greater than 0, okay, or let us say a1 is greater than 0, then this term is negative, which means that a3 minus a1 has to be less than 0. Now, if a1 is less than 0, then this term becomes positive, and then a3 minus a1 has to be greater than 0. Okay. The first condition implies a3 less than a1, and second condition implies a3 greater than a1. Okay. So, the constraints on a3 and a1 can be written like this. Okay. So, these are your constraints on a3 and a1 if the condition has to hold, which is given in the problem. Okay. Now, the next problem that we consider is the balance of angular momentum, but now we consider the distributed moment field. So, we saw that under the action of external loads, that is without any body moments, the Cauchy stress tensor came out to be symmetric. Okay. When we applied the balance of angular momentum, we saw that the Cauchy stress tensor in the absence of any body moment turned out to be symmetric. Now, you consider a case where the body is subjected to a distributed moment field m, okay, the vector m per unit volume about an axis parallel to the E2 direction, which means that m is me2, m is the component of this vector m along the E2 direction. Now, you have to show that the Cauchy stress tensor will no longer remain symmetric. Okay. To show that, we first state the moment of momentum principle. Okay. Which states that the law of conservation of angular momentum states that the change in angular momentum of a body is equal to the resultant moment applied to it, and mathematically you can write this as the material time derivative of the angular momentum should be equal to the resultant moment applied on the body. Okay. Now, the angular momentum of the body is integral over the volume x cross rho x dot. Okay. That is the linear momentum. Okay. So, rho is the density, x dot is the velocity, and dv is the volume. So, rho dv is infinitesimal mass dm. Okay. So, x cross dm x dot, that is the linear momentum, gives you the total angular momentum. The net external moment will be the moment because of the body forces, the moment because of the surface tractions, and now you will have one term. This is nothing but the moment, okay, the distributed moment which has been applied over the bulk of the body. So, you will have this term, and remember we do not have this x cross here because m already is a moment, okay, per unit volume. So, we just need to multiply by the infinitesimal volume, and we have to integrate over the volume of the body. Okay. If we substitute these here in equation 1, okay, so substituting the expression for angular momentum and applied external moment in conservation of angular momentum equation, and then expressing in initial notation, we get that the material time derivative of the moment of linear momentum should be equal to the moment of the body forces plus the moment of the surface tractions plus the distributed moments. Okay. Now, using Reynolds transport theorem for extensive quantities, okay, we can take this inside, and then we can apply the Gauss divergence theorem to convert this integral over surface as to integral over the volume. So, we get the total distributed moment plus the moment of the body forces should be equal to epsilon I j k sigma k j x j sigma k l comma L. Okay. Now, I can take this term and I can take this term and I can apply the equilibrium equation. Okay. So, I can take this term here, and this is the equilibrium equation, which means this equal to 0, and then I have the remaining two terms, this term and this term. Okay. So, this is the one term which is remaining, and this is the moment because of the external distributed moment acting over the body. Okay. So, now balance of linear momentum says this is equal to 0. So, I have already said the first term in the integral goes to 0 and we are left with following expression. Okay. That following expression, and then we take both the terms inside and then we have the integral over the volume, the term in the bracket equal to 0. Now, the volume is arbitrary, therefore, this integrand over here has to go to 0. Okay. So, integrand must be equal to 0, which implies that epsilon I j k sigma k j plus m I equal to 0. And now, I is a free index here and k and j are repeated index. So, therefore, I takes 3 values 1, 2, 3. Okay. So, there are 3 equations. So, for I equal to 1, you have epsilon 1 j k sigma k j plus m 1 equal to 0. For I equal to 2, you have epsilon 2 j k sigma k j plus m 2 equal to 0, and for I equal to 3, you have epsilon 3 j k epsilon k j plus m 3 equal to 0. Okay. Now, we do the summation over j n k, okay, in each of these terms. Okay. And when we do this, we find that epsilon 1 2 3 sigma 3 2 plus epsilon 1 3 2 sigma 2 3 equal to 0. This is the second term, okay, and this is the third term. So, this implies that sigma 3 2 minus sigma 2 3 equal to 0. This is because epsilon 1 3 2 equal to minus epsilon 1 2 3, and this we substitute here, and then epsilon goes out and we will have following expression. This is the second expression and this is the last expression. Okay. So, what we see here is sigma 3 2 is equal to sigma 2 3. However, we see that sigma 1 3 plus a moment m 2 will be equal to sigma 3 1 and sigma 2 1 is equal to sigma 1 2. Okay. So, now we see that although the out of the 3 shear components 2 are same, but sigma 1 3 is not equal to sigma 3 1. It is sigma 1 3 plus m 2 equal to sigma 3 1. Okay. So, we finally conclude that the conservation of angular momentum implies that the Cauchy stress tensor for a body subjected to distributed moment is not symmetric, which means sigma I j is not equal to sigma j I, or in direct notation sigma not equal to sigma transpose. Okay. So, this example shows that if you have distributed moments over a body, then your Cauchy stress tensor will no longer remain symmetric. Okay. So, next we consider the final example, and which is you have an incompressible bar of uniform length and initial area A 0, which is lying along the x 1 axis loaded by a force F along the axis, and the bar stretches by a factor of alpha. Okay. And the bar is free to deform in the other 2 direction, that is in E 2 and E 3 direction, that is x 1, x 2 and x 3 direction. And for this you have to find out the value of the maximum shear stress and the location in the spatial configuration of the maximum shear stress if the Cauchy stress tensor sigma 1 1 is given by alpha f by A 0. Okay. And the orientation of the plane of maximum shear stress in the material configuration. Okay. So, first you have to find out this in the spatial configuration and then you have to find out this in the material configuration. Okay. So, now let the maximum shear stress acting on the plane whose normal is n is given by cos theta sin theta 0. Okay. And from Cauchy stress principle we know that T equal to sigma n, and now our sigma is given by following expression. Okay. Apart from sigma 1 1, everything else is 0, n is cos theta sin theta, therefore, our traction T vector is nothing but alpha f cos theta by A 0 0 0. Now, I can compute the normal and shear component of the traction vector as this. So, the normal component, okay. So, you have a plane whose normal is n and then there is a traction vector T which acts. Okay. So, you will have a normal vector T n and you will have a shear traction T s. Okay. So, finding out this normal, you have to take the projection along the n, which means you have to compute t dot n, and then to get the vector you have to multiply by the unit vector along that direction. Okay. So, the normal traction is t dot n into n, and then shear. Okay. So, now this is this is shear and this is normal and this is t. So, using triangle law I know that t is T n plus T s. Okay. So, T s here will be T minus T n. Okay. So, the shear traction is total traction minus the normal traction. Okay. So, if I do this, I can find the normal traction by this expression and the shear traction by following expression. Now, if T s changes with theta, then there is certainly there is a value of theta for which T s acquires a maximum value. So, I first need to find out the magnitude of T s, and I can find out the magnitude of T s as norm of T s, which is nothing but alpha f by 2 a 0 sin 2 theta. Okay. So, for maximum shear stress, the dt by d theta should be equal to 0. Sorry, this is S. Okay. So, we have to take dTs by d theta. Okay. So, d by d theta of this quantity, and if I do this, I get alpha f a 0 cos 2 theta equal to 0. Now, alpha is given, f is given, a 0 is given. Therefore, for this to be maximum, cos 2 theta has to be maximum, which is maximum when 2 theta is pi by 2 plus m pi, which means 2 theta is equal to 90 degree for m equal to 1, or theta is equal to 45 degree. Okay. So, if I put theta equal to 45 degree in the expression for T s, I get my maximum shear stress as alpha f by 2 a 0. Okay. So, if you just put theta equal to 45 degree here, sin 2 theta, which is sin 2 into 45, sin 90 degree, and sin 90 is equal to 1. Therefore, the maximum value of the shear is alpha f by 2 a 0, and that is what we have here. Okay. So, now you know the maximum angle at which the shear stress happens in the spatial configuration, and this is the maximum value. Now, part B of this problem, I leave it to you as an exercise. You try it yourself, okay, and you try to find out what is the value of theta in the material configuration for which the shear is maximum. Okay. Remember, you have a bar, you apply force and it deforms. Okay. So, in the deformed configuration, we have found out this value of theta as 45 degree. However, this plane will be different in the material configuration corresponding. So, this is say small a, small b, and this is capital A, capital B. So, this is the material configuration time t equal to 0, this is a spatial configuration. Now, this plane after deformation will go to plane AB. Okay. So, we need to find out what is this value of theta prime. Okay. So, the part B of this problem, I leave it to you as an exercise. Okay. Thank you.